Okay, let's unpack this. We are diving into one of the most aggressive and, frankly, challenging cancers out there.
Oh,
Triple-negative breast cancer, or TNBC.
that's right. And the real challenge isn't just treating it, but figuring out why the same cutting-edge therapy can work brilliantly for one patient and then do almost nothing for another.
That variability is the whole mystery, isn't it? I mean, TNBC is defined by what it lacks.
Exactly. It doesn't express the estrogen receptor, progesterone receptor, or HER2 protein, so your standard targeted therapies are just off the table.
And yet, here's the contradiction. It's actually the most immune-responsive subtype of breast cancer.
It seems like it should be an easy target for the immune system. But when you use a standard immune checkpoint drug on its own, like pembrolizumab, which we'll just call Pembro, the success rate is, well, it's low, maybe 20% in the metastatic setting.
So it's a promising hammer, but it only hits the nail some of the time.
Perfectly put. So our mission today is to figure out what predicts success. We're deep diving into a clinical trial that combined Pembro with targeted radiation therapy.
The idea being that radiation could sort of jumpstart the immune response.
Precisely. To act as a spark plug. We're going to track the tumor's immune microenvironment, the TME, over time to see exactly who responds and why.
And this all comes from a neoadjuvant trial, so that's treatment before surgery. Let's set the stage because the timing here is really, really important.
It is. It's a beautifully designed trial for collecting this kind of data. First, patients got a cycle of just Pembro.
Okay, just the immunotherapy.
Then 3 weeks later, they got a second cycle of Pembro, but this time with focal high-dose radiation. Only after that did they move on to standard chemo and surgery.
And crucially, the researchers got biopsies at 3 different points in time.
Yes. You have your starting line, which is baseline. Then you have a check-in after Pembro alone, which they call PD-1.
And then the finish line for this part of the study after the combo.
Right, which they call RT-PD-1 after Pembro and radiation.
So did the strategy work? Clinically speaking.
It worked remarkably well. Almost 2/3 of the patients, about 67%, had either a complete response, meaning no cancer left, or just minimal residual disease.
And that's way higher than you'd expect from Pembro alone or chemo alone.
Oh, absolutely. Those are usually around the 40% mark. So this synergy, this combination effect, it's very real.
So how do you prove what's causing that synergy? You have to see what's happening inside the tumor at a cellular level.
This is where they brought in the heavy artillery. They used 2 massive techniques to understand both what the cells were doing and where they were located.
Okay, break those down for us.
First, they took over 500,000 immune cells and analyzed them with single-cell RNA sequencing, or cRNA-seq.
So that's like reading the individual instruction manual for every single cell to see if it's active or tired or...
Exactly. Is it naive? Is it an effector? Is it exhausted? That tells you the state of the cells. But you still need the map.
You need to know what they are in the neighborhood.
Precisely. And for that, they used a technique called Codex. It's a type of spatial proteomics that mapped 5.4 million cells, showing their physical location and who they're next to.
So cRNA-seq says, we have a lot of killer T cells.
Right. And Codex says, and those killer T cells are clustered right up against the tumor, talking to a very specific kind of macrophage. It's the difference between a list of residents and a city map.
I love that. And to make sense of that incredibly dense map, they used machine learning to find recurring cellular neighborhoods.
They did. They used an algorithm to group cells based on who their neighbors were, and they called these recurring communities districts.
Districts.
They found 12 distinct districts. Some were mostly tumor cells, but the interesting ones, of course, were the immune neighborhoods.
All right, let's do a quick recap here. We have a successful combo therapy in TNBC. We're using single-cell tech to see what cells are doing and spatial tech to see where they're located. And this has revealed 12 cellular districts.
And that brings us to the big question. If you look at that map before any treatment, can you predict who's going to respond?
So what did that baseline snapshot tell us? Was it just that responders had more immune cells to begin with?
Not quite. And this is a really key point. The total number of immune cells didn't really separate the responders from the non-responders.
Okay, so it's not about quantity.
It's about density.
Oh.
How closely packed those cells were in specific areas. Responders had a much higher immune cell density. Location, location, location.
And was there one specific dense neighborhood that was the crystal ball?
There was a B-cell dominant neighborhood. They called it District D4.
D4.
At baseline, before any treatment, D4 was the only district that was significantly higher in patients who eventually responded. This little area, about 54% B cells, was a hugely powerful predictor.
So if your tumor already had this B-cell-rich training camp, let's call it, you were primed for success.
That's the idea. It suggests the immune system had already started to organize itself. In fact, the presence of that spatial district correlated perfectly with having specific, naive, and memory B cells in the single-cell data.
It all connects. Now, let's fast forward to after the combo therapy. What did the map look like in the people who responded successfully?
Well, first, the tumor cell districts, they just vanished, a clear sign of tumor clearance. And in their place, you saw this influx of immune cells.
The troops moving in?
Exactly. A surge in cytotoxic CD8 plus T cells and plasma cells. And several new immune districts became dominant, particularly a T-cell-rich one, and, very importantly, a myeloid-dominant district called D9.
Okay, so the T cells are the soldiers. But they need orders, right? What was the critical interaction that fueled their attack?
Right. A T cell can't do it alone. The researchers found that the expansion of the most effective tumor-killing T cells was spatially correlated, meaning they were physically interacting with a very specific type of immune manager.
And that would be?
The antigen-presenting macrophages. Specifically, a subcluster they labeled CM11.
So the T cells can't just flood the zone. They need these macrophages to, what, point out the enemy.
That's exactly it. These macrophages are like the drill sergeants. Radiation helps create a lot of tumor debris. These macrophages gobble it up, process the cancer antigens, and then physically present those antigens to the T cells.
Ah, so that's the antigen presentation.
It is. And that communication tells the T cells exactly what to kill, and it massively amplifies their response. That local dialogue is the engine of the whole thing.
Wow. Okay, so to sum up this part, a B-cell neighborhood at the start predicts success. And that success is driven by T cells getting orders from these specific macrophages after the combination therapy.
You've got it. But here is where the story gets really, really cool. When they looked at all the data, they realized the responders weren't one big group.
They split?
They split. The successful patients fell into two completely distinct subgroups. And these groups align perfectly with the classic cancer immunity archetypes: inflamed, excluded, and ignored.
Okay, let's start with the non-responders, the NR group. These will be the ignored tumors.
Yes. They are immunologically silent. They had very few immune cells to begin with, and they barely changed after treatment. But crucially, the tumor cells themselves were actively hiding.
How so?
They had very low expression of MHC proteins. MHC is the flag that a cell waves to say, hey, I'm infected, or hey, I am cancerous. If you don't wave the flag, the immune system just walks right by.
Completely ignored. Okay, now for the winners. Let's talk about responder group 1, or R1.
R1 is the inflamed archetype. These tumors were basically set up to win from the very beginning.
I came prepared.
Totally. At baseline, they were already packed with B cells, plasma cells, and T cells. And their tumor cells were waving those MHC flags like crazy. They were primed and ready to fight.
So what did their response trajectory look like?
They responded early, and they responded to pembro alone. You could see the tumor cells starting to disappear after that first biopsy, before radiation was even added.
So for them, the immunotherapy by itself was enough.
It seems so. And what's fascinating and maybe a little cautionary is that adding radiation didn't seem to help them. In fact, their B-cell-rich D4 districts, our predictive marker, actually got depleted after RT.
Why would that happen?
B cells are just very sensitive to radiation. So for this R1 group, the R key might have been unnecessary or maybe even a little detrimental to their pre-existing immune structure.
Wow. Okay. That leaves the most interesting group. R2, the excluded or late responders.
This is the group where the synergy really shines. At baseline, you could not tell an R2 tumor from a non-responder.
Really? They look the same.
Almost identical. Low B cells, low T cells. It fits the excluded phenotype where immune cells are kind of stuck on the edges of the tumor but can't get in.
A cold tumor, basically. So how on earth did they end up with a complete response?
The response was delayed, and it was maximal only after the combination of pembro and radiation. The tumor clearance, the explosion of immune cells, it all happened after RT-PD1. The combination therapy was the spark that lit the fire.
So RT was the essential ingredient to turn that cold tumor hot. How did the data confirm that?
It came back to that critical partnership. In the R2 group, you saw this massive expansion of killer T cells, but it was paired with a dramatic spike in the proportion of those antigen-presenting macrophages, the CM11 cluster, only after radiation.
So radiation brought in the drill sergeants.
It seems to have created the conditions for them to thrive. The spatial link between the T cell districts and the myeloid districts became strongest in R2 only after RT. Radiation damages the tumor, the macrophages clean it up and present the pieces, and that finally teaches the excluded T cells how to get in and fight.
That is just such a clear, robust mechanism. But to really lock this down, they took it to the lab, right? To a mouse model.
They did. You can't prove synergy in a single-arm human trial, so they used a mouse model of TNBC. And the survival data was just unambiguous.
What did it show?
Pembro alone or RT alone gave you maybe 20 to 30% long-term survival. The combination,
Let me guess.
100% survival. Complete tumor regression. It proved the biological synergy they saw in the human R2 group was real.
And did the mechanism hold up in the mice? Did they see the same macrophage shift?
Perfectly. The cRNA-seq on the mouse tumors showed that radiation did two things. First, it boosted the T cells. Second, it caused a huge shift in the myeloid cells toward an antigen-presenting phenotype with macrophages that looked almost identical to the human CM11 cluster.
So the conclusion is validated. RT is the key that unlocks the response in these excluded tumors, and it does it by revving up the antigen-presenting macrophages.
And that has massive clinical implications. The R2 group represents the exact kind of tumor that normally fails immunotherapy when it's given alone.
So we basically have a potential roadmap now. If we can use baseline markers to tell an R2-like tumor from an R1-like tumor,
You can guide them to the right treatment from day one. Think about the standard of care right now. It's often pembro plus really toxic multi-agent chemo. The rate of severe side effects is almost 80%.
that's incredibly high.
It is. This study suggests that for a big group of patients, the R2s, we could use focal RT instead, achieve a great outcome and potentially spare them from some of that systemic toxicity.
That's the real promise of personalized oncology, isn't it? We started by saying not all responses are the same, and we found the reason why. R1, the inflamed tumor that was ready to go, versus R2, the excluded tumor that needed RT to kickstart the response.
It fundamentally changes how we should look at a tumor. But it also leaves us with a really critical strategic question to think about.
Go on.
If radiation seemed to be, maybe not helpful for the R1 group, the ones who were already inflamed and had those radiosensitive B cells, should we be thinking about de-escalation for them? Maybe they only need the immunotherapy.
And conversely, you would only intensify the treatment, adding the radiation for the R2 excluded phenotype who clearly needs it.
That's the provocation, right? Can we use this detailed map of the tumor microenvironment to precisely tailor the intensity of our treatments, to maximize the benefit for everyone while minimizing the harm? It's a question we're now, finally, equipped to start answering.
A perfect illustration of how mapping these cellular neighborhoods can change everything. Thank you for guiding us through this amazing deep dive.